In Chapter 14, we will investigate the relationship between two quantitative variables using a scatter plot, which is a type of graph, and the correlation, which is another numerical quantity. These are the concepts that we will discuss in Chapter 14: scatter plots, interpreting scatter plots, and understanding correlation. Most statistical studies examine data on more than one variable. Fortunately, statistical analysis of several variable data builds on the tools we have used to examine individual variables. The principles that guide our work remain the same. We'll first plot the data, then add numerical summaries. We'll look for overall patterns and deviations from those patterns. And when the overall pattern is quite regular, there is sometimes a way to describe it very briefly. So let's now discuss one of the most common ways to display the relation between two quantitative variables, called a scatter plot. A scatter plot shows the relationship between two quantitative variables measured on the same individuals. The value of one variable appears on the horizontal axis, and the value of the other variable appears on the vertical axis. Each individual in the data appears as the point in the plot fixed by the values of both variables for that individual. For instance, in the scatter plot to the right, each point represents an individual in our data set. For each individual, we know its distance and velocity. The value of these variables determines the position on the scatter plot. Now, when we make a scatter plot, we'll always plot the explanatory variable, if there is one, on the horizontal axis. As a reminder, we usually call the explanatory variable x and the response variable y. Now, if there is no clear explanatory and response distinction, either variable can go on the horizontal axis. So let's outline the steps to making a scatter plot. First, decide which variable should go on each axis. If a distinction exists, plot the explanatory variable on the x-axis and the response variable on the y-axis. Then, label and scale your axes. And finally, plot the individual data values. Now you try one. For centuries, people have associated intelligence with brain size. A recent study used magnetic resonance imaging to measure the brain size of several individuals. The IQ and brain size of 6 individuals are as follows. Is there an explanatory variable? If so, what is it and what is the response variable? Finally, make a scatter plot of these data. So pause the video and unpause when you're ready for the answer. In this case, brain size is the explanatory variable and IQ is the response variable because brain size is what we think is causing the change in IQ. Because of this, brain size will be represented on the horizontal axis and IQ on the vertical axis. After labeling and scaling each axis, we begin plotting the 6 points. The first individual had a brain size of 100 and an IQ of 140, so we plot a point at the pair 100, 140. If we do this for all 6 individuals, we get a final scatter plot that looks like this. So let's talk about how we interpret what we see on a scatter plot. Just as with any other graph of data, we're going to look for an overall pattern and for striking deviations from that pattern. You can describe the overall pattern of a scatter plot by the direction, the form, and the strength of the relationship. An important kind of deviation is an outlier, an individual value that falls outside the overall pattern of the relationship. For example, figure 14.4 is a scatter plot of the gas mileages and the weights of 38 cars. The response variable is gas mileage, and the explanatory variable is weight. We see that gas mileage decreases as weight goes up. So in this case, we would say that figure 14.4 shows a negative association. In general, the direction of a scatter plot can be described in terms of a positive or a negative association. Two variables are positively associated when above average values of one tend to accompany above average values of the other, and below average values also tend to occur together. On a scatter plot where the data is positively associated, the scatter plot will slope upwards as we move from left to right. Two variables are negatively associated when above average values of one tend to accompany below average values of the other, and vice versa. Scatter plots of data that show a negative association have a negative slope. So let's return to our scatter plot comparing brain size and IQ. What is the form, direction, and strength of the association? And are there any outliers? The direction of this relationship is positive. As brain size increases, so does IQ. There is a moderately strong straight line relationship if you exclude the two possible outliers. A scatter plot displays the direction, form, and strength of the relationship between two variables. Straight line relations are particularly important because a straight line is a simple pattern that is quite common. A straight line relation is strong if the points lie close to a straight line, and weak if they are widely scattered about a line. However, our eyes are not very good for judging how strong the relationship actually is. Because of this, we need to follow our strategy for data analysis by using a numerical measure to supplement the graph. And this is where correlation will come in. The correlation describes the direction and strength of a straight line relationship between two quantitative variables. Correlation is usually written as an R. Calculating a correlation takes quite a bit of work. If the data set is quite large, we'll often use a calculator or computer. Knowing how we obtain R from data, however, does help us understand how correlation works. This is the formula that we will use to compute correlation. It will be explained in the next example. So let's do an example where we compute the correlation between two variables. Here we will compute the correlation between femur length and humerus length. Here we will regard femur length as the explanatory variable. First, we must compute the mean and standard deviation for both variables. In this case, the mean femur length of the 5 observations is 58.2 centimeters, with a standard deviation of 13.2 centimeters. The mean femur length is 66 centimeters with a standard deviation of 15.89 centimeters. Next, we must compute the standard score for each observation for both variables. If you recall, the standard score is defined as the observation minus the mean divided by the standard deviation. For instance, the standard score for the first femur length is negative 1.530, and the standard score for the first humerus length is negative 1.573. Next, we multiply the standard scores for each pair and add each of these products. In this example, we have 5 pairs, so there will be 5 terms in this sum. Finally, we'll divide this sum by the number of pairs minus 1, which in this case is 4, to arrive at the correlation. In this case, R is equal to 0.994. So let's summarize some of the basic facts about correlation. Positive values of R indicate positive association, and negative values of R indicate negative association. The correlation will always fall between -1 and +1. The correlation equals -1 if all the points fall on the same line of negative slope. The correlation equals +1 if all the points fall on the same line of positive slope. The correlation does not change when we change the units of measurement. Correlation ignores the distinction between explanatory and response variables. Correlation measures the strength of only straight line association between two variables. And finally, the correlation is strongly affected by a few outlying observations. For instance, in this first scatter plot, the correlation is 0. The data points don't show a linear trend and seem mostly randomly scattered. In the second scatter plot, the correlation is -0.3. This is supported by the fairly weak negative association shown. In the third scatter plot, the correlation is 0.5. There is a slightly stronger linear relationship than the previous scatter plot, although the data shows more of a positive association this time. In the fourth scatter plot, the points show a fairly strong negative association, and the correlation is -0.7. In the fifth scatter plot, the correlation is 0.9. The data points show a strong positive association. Finally, the correlation is -0.99 in the last scatter plot. The points are almost all on the same line. These data show a very strong negative association. Let's look at an example that shows how sensitive R is to outliers. Recall our example where we showed the correlation between femur and humerus length was 0.994, indicating a very strong positive association. Suppose the observation around 40-40 was closer to 60-40. How would this affect the value of R? In this case, the value of R would be 0.64, indicating a much weaker positive association. It is because of examples like this that we often omit outliers when describing overall general trends. So let's close the lecture today by making a few comments about the usefulness of correlation. There are many kinds of relationships between variables and many ways to measure them. Although correlation is very common, remember its limitations. First, correlation makes sense only for quantitative variables and not categorical. Even for quantitative variables, such as the length of bones, correlation measures only straight line association. Correlation is not a complete description of two variable data, even when there is a straight line relationship between the variables. Finally, you should give the means and the standard deviations of both x and y along with the correlation.